Let's take a look at exam 3, problem 2. So in problem 2 we have a coaxial cable. This is the kind your television uses all the time, and what we want to look at is, and in this one, the inner radius is RA, the outer radius is RB. The inner conductor has a current coming straight out of the page at us, and the outside conductor, or sorry, yeah, inner conductor is coming out of the page. The outside conductor has the same current headed into the page. All right. So if you look at this, I asked for use symmetry of the problem in Ampere's law to determine magnetic field direction and magnitude for R less than A, R greater than RA, but less than RB, and RB greater than R. Okay. So if you go inside here, and you think about, I'm going to use Ampere's law, which means I'm going to go, because the problem is symmetric, radially symmetric. If I go in a circle, in Ampere's law, let's pull it over real quick. Oh, oh. Ampere's law says that integral of B dot dl along a closed path is mu naught times the total in current flowing through that surface. All right. So if we look at this and we look at the middle of this and we think about we're going to go in a circle through here, and it's going to enclose the total current in there. Well, what's the total current inside of here? Well, the answer is 0. So if we do R less than RA, right? Then B, doesn't matter if it's a vector or not, is 0. All right? Okay. So now we're going to go again in a circle. And I'm going to go in a circle this direction. Why? Because by the right-hand rule, the current coming out of the page indicates that the magnetic field would be a circle going counterclockwise. All right? So I'm going to go in a circle around this counterclockwise. And if this circle, if I could draw better, all right, if I could draw better, and this circle were actually centered on the inner conductor, right, instead of wobbling all over the place like this one, then the B field anywhere along that would in fact be constant, right? So I could write this, I could rewrite Ampere's law as B, and it's going to be in the phi hat direction. Phi hat is basically the direction of the angle unit vector, but B times the integral of just R d phi. Let me back up a step and write a little more formally. B vec equals B phi hat, right? So it's a unit vector pointing along the circle. dl equals dl phi hat. So it is a differential step along the circle, and the length of it is r d phi, d hip, yes, r d phi in the phi hat, right? Phi hat direction, r d phi. So dl equals r d phi. B is in the phi hat direction. dl is in the phi hat direction. That gives us right, the integral around the loop, b vec c dot dl vec equals b times r, because r is also not a function of, well, let me do this first. OINT. So b.dl is just br d phi. All right, br d phi. And it's br d phi because the phi hat dotted with the phi hat is 1. And so the loop, the integral around the whole loop, is an integral from 0 to 2 pi of br d phi. The only thing in this integral that depends on phi is d phi. So this is, we can write more simply, 0 to 2 pi of d phi. All right? And the integral of phi, d phi is just phi, so this is br phi. All right, integral d phi is phi. Evaluated, right, from 0 to 2 pi. Oh, always love it when I get out of the mode I want to be in. Evaluated from 0 to 2 pi. Oh, still didn't work. Okay, so phi evaluated from 0 to 2 pi, which I've not been able to get it work. Let me back up. Just, there's my problem. Okay. From 0 to 2 pi. Still not working? Okay, so we have to evaluate phi from 0 to 2 pi, which is just 2 pi minus 0 equals br 2 pi. So now we know that 2 pi br equals mu naught I. And so that inside of that, in between the two conductors from RA to RB, B equals mu naught I divided by 2 pi R in the phi hat. Yes, if I could do phi hat correctly. Phi hat direction. And that is the solution for, let me put this in here, R sub A less than R sub B. Okay, so that's the second part. My apologies for all the typing issues. The third part, we're asking, all right, now we're going to come all the way out here. We're going to come all the way out here and hopefully draw a real circle around everything. And B.L equals the total current flowing inside. But we have here a current coming out of the board, and we have here a current going into the board, or into the page, and they're the same magnitude. So when you come out here, the total current flow in the conductor, total current flow in the coaxial cable is 0. All right, so when you get out there, you're back to the solution that for RB, right, less than R, B equals 0. And that is the answer to problem 2.